Very good morning to all. Let's start the basics about heat treatment. As we know that heat treatment process is a series of operations which involving the heating and cooling of metals in the right. Mostly we know that the purpose of heat treatment is to change the mechanical properties or combination of mechanical properties so that the metal will be useful. Either it may be the objective like serviceability, or it may be used for the safe for definite any purpose, right? So we are trying to heat treatment, or by with the help of heat treatment, what happened to the metal? Metal can be either made harder, stronger, right? Or as per the criteria, or as per the application, it may increase or raise the impact. Same way, sometime it may be more ductile, or sometime it may be metal is more softer. So that are the main objective of the heat treatment. Now, no one heat treating operation can produce all of these characteristics. ऐसा नहीं है कि सारे कैरेक्टरिस्टिक जो है वो सभी एक ही हीट ट्रीटमेंट से आते हैं, राइट? सो as per the requirement we are use different kind of heat treatment processes, and as per the application we are prefer, or we are select the different kind of heat treatment process. Okay, as uh, the one figure is given to you, so you can understand that what kind of processes done in the treatment. The first one is the annealing, normalizing, quenching, tempering, surface hardening, case hardening, wash tempering, mark quenching, and osmoforming. Now we discuss all in one by one. Annealing, as we know that softening the material. What they do, they for annealing we are prefer for soft the material, or to bring about required changes in the properties. Which kind of properties? Like machinability, mechanical or electrical properties, or dimensional stability. If we achieve, or if we want to sustain for machinability or mechanical properties, then we prefer to use the annealing process. In annealing process, what happen in the annealing process? It may heating the steel, or go near to the critical temperature, and to make it suitable for fabrication. A material can be annealed by heating it to a specific line, and then material can slowly cool to room temperature. You just remember that it may cool slowly to the room temperature in oven. You can just refer the diagram where temperature versus carbon content is given to you. Here you can see that the yellow portion is indicated with the austenite, while this orange portion is the mixture of austenite and cementite, right? As we know in the iron carbon diagram. So when an annealing cool in the furnace, if it may allow in the furnace to cool, then it known as a full annealing. Sometime it may be asked in your important. Most probably, we are prefer to use the normalizing process in the ferrous metal. If it differ from the annealing in that the metal is heated to a higher temperature and then removed from the furnace for air cooling. Okay, initially start for refrigerating temperature. Okay, means above 720 degrees Celsius, and then remove from the furnace for air cooling. उसको furnace में से निकाल के कहाँ पे हम cool करते हैं? Definitely it may be cool in the air. The purpose of the normalizing is to remove the internal stresses. Most probably we prefer to use the normalizing process in heat treatment like welding, casting, forging. Okay, so that all the after this all the basic process, we have preferred to use the normalizing process. If you see the normalizing process mostly in the plate mills, in the production of large forgings such as railroad wheels, axles. Okay, so we have preferred to use the normalizing process. Definitely, the cost of this is comparatively less than annealing process. Okay, you can see here above the recrystallization temperature, we are prefer to use in this area where normalizing is proceed. Next one is the hardening process, or it may be also known as a quenching. It is done to increase the strength and wear properties. Most probably, when we are prefer to use quenching or hardening process, when we have to achieve good strength or good wear properties. Okay, one of the prerequisite for hardening is sufficient carbon and alloy element, which are very important. That carbon are very sufficient content is available. So then and then it is preferred to use this quenching process. To harden by quenching, a metal must be heated into a austenitic crystal phase and then quickly cool. Okay, it mostly cool very quickly. But if you talk about the annealing, then the quenching is done or the cooling is done slowly. Okay, so depending on the alloy and the other consideration, the cooling may be done with force of air or other gases like nitrogen. Okay, so here the cooling is done either with the forcefully, means with the help of nitrogen or any gases, or with the help of some polymer dissolved in the water or in the brine. So this is the basic difference that also you may remember, that how it may be cool in the normalizing process or in the annealing process or in the hardening process. Okay, but there is one basic disadvantage, that when we cool it very fast, due to that what happen, it may become brittle. Okay, this treatment is therefore typically followed by tempering process, which is a heating process at another lower specific temperature, which relieve the stresses the material and minimize the brittleness problem. Okay, what we have to do, we have to use the tempering process. So इससे क्या होता है, इससे the temperature heating process at another lower specific temperature. Okay, वो क्या करेगा कि एक दूसरा टेम्परेचर लेगा, वहां पे वो स्ट्रेस रिलीव करेगा. ड्यू टू दैट व्हाट हैपन, the brittleness जो disadvantage, it may reduce in some cases. Okay, next one is the case hardening. In case hardening is the process of hardening the surface of a metal, often low carbon steel, by infusing element into a material surface, forming a thin layer of harder material or alloy. Case hardening improves the wear resistance of machine parts without affecting the tough interior of the part. So you can see that these are the one example. This is one of the example of case hardening process. Now, OS tempering. OS tempering is heat treatment that is applied to ferrous metal, most notably steel and ductile iron. In steel, it is produce a binite microstructure, whereas in cast iron, it produce a structure of acicular ferrite and high carbon stabilized austenite, which is known as a osferrite. It is primarily used to improve mechanical properties or reduce, or it may eliminate the distortion. Okay, so that we have to remember where it may be used, which is very important for us. I just show you one video regarding the process which we are use in heat treatment, and after the remaining portion I will try to finish. Let's see the video, so it may very helpful to you understand that how the process may done in its
How do we tailor the properties of steel for a desired application? How can we make a metal strong or tough? How can we optimize properties? And what information can help in defining how we heat treat metals? In this video, we will try to answer these questions by looking at how heat treatment is critical in achieving the optimum properties and how we can either soften or harden a metal through producing different microstructures. We will review the different heat treatments, the microstructures formed, and how we predict what these might be. Along with the addition of chemical elements, heat treatment is probably the most important process in controlling the properties of metal. It involves heating solid metal to a defined temperature, followed by a suitable cooling rate in order to achieve the desired material properties. Heat treatments are primarily conducted to either soften or harden the steel, depending on its final application and manufacturing process. This softening treatment is often referred to as a conditioning process and will lower strength and hardness while increasing toughness and ductility. Conditioning includes two heat treatments, cold annealing and normalizing. The hardening process does the opposite. It increases strength and hardness while lowering toughness and ductility. This includes two processes called quenching and tempering and age hardening. The specific heat treatment used in manufacturing will depend on the metal chemistry, the size of the part, and the required properties. The three main structures that are achievable through heat treatment are perlite, bainite, and martensite. For the majority of heat treatments, we cool from the austenitic temperature region. The austenitic region is where most of the alloying additions go back into solution, and this is shown here in the iron-carbon equilibrium diagram. This diagram shows the structures formed under slow cooling in iron as a function of temperature and carbon content. As we cool through the transformation region, we can create different structures by altering the cooling rate. If we want to achieve perlite, the softest structure, we need to cool slowly enough so that this is formed. To achieve martensite, the hardest structure, we need to cool quickly enough to ensure that perlite or bainite is not formed. The speed of these cooling rates depends on a given steel composition, and there are various diagrams that help to predict the different structures formed. These will be discussed later in this module. Quench and tempering is probably the widest used of the heat treatments to harden steel and consists of heating the material to approximately 15 degrees Celsius or 60 degrees Fahrenheit to the austenitic range. For steels, this is usually somewhere between 700 degrees to 1000 degrees Celsius or 1290 degrees to 1830 degrees Fahrenheit. It is then held at this temperature until the material is fully transformed to austenite. This hold time takes into account the dimensions of the component. The material is then removed from the furnace and submerged, usually in an agitated liquid, in a process called quenching. This causes changes in the microstructure as the component cools rapidly down to around 200 degrees Celsius or 390 degrees Fahrenheit. This quenching causes none or very little carbon to precipitate as iron carbide. It produces a feather-like structure called martensite, which distorts the internal structure. This additional stress makes it difficult for defects on the atomic scale, called dislocations, to move around in response to the applied load, causing the material to become stronger. The formation of martensite is only achieved if the material exceeds a critical cooling rate. If not, the microstructure formed will be either bainite, perlite, or ferrite, or a combination of these. This is the reason why components of different sizes processed the same way may have vastly different properties, and also why the surface properties may differ from the center, which would cool slower than the surface. The quenching operation will increase the hardness and strength of the steel, but will drastically decrease the ductility and toughness. The aim of tempering is to soften the steel back, achieving the desired combination of properties. Tempering will considerably improve toughness and ductility while still maintaining a high strength level. Tempering consists of heating the steel to a temperature below the austenitic range, usually somewhere between 500 degrees to 650 degrees Celsius or 900 degrees to 1200 degrees Fahrenheit, and holding at this temperature for a specific time period. During this process, the hard, brittle martensite dissociate into ferrite and iron carbide, producing a structure called tempered martensite, which has lots of fine particles dispersed through the ferrite. This will give the optimum combination of strength, hardness, toughness, and ductility. The ratios of these properties can be refined through the time and temperature of the tempering. Age hardening, sometimes called precipitation hardening, is used to increase the strength and hardness of some stainless steels and nickel-based alloys. It follows similar steps to quench and tempering in such that the material is heated to a temperature to dissolve all the atoms into solution. It is then quenched at a cooling rate fast enough for the atoms to remain frozen in solution. The final step differs from tempering as it is designed to harden the steel as opposed to soften it back. It is called aging and involves the controlled reheating to around 450 degrees to 650 degrees Celsius or 840 degrees to 1200 degrees Fahrenheit to cause some atoms to precipitate. These create strain in the structure, and again this makes it difficult for the dislocation effects to move in response to the applied load, making the material stronger.
To the tempering process, post tempering process, we are explained with the video also. So now start with the tempering. Tempering is carried out by preheating previously quenched or normalized steel to a temperature below the critical range. Then holding and then cooling to obtain the tempering is used to reduce the brittleness of quenched steel. The temperature choose for the tempering process directly impact the hardness of the workpiece. So the higher the temperature in the tempering process, it's okay. So that is very important, and that's why the temperature is somewhat less. Okay, which can very easily understand in the TTT diagram with the product is benite. Now surface hardness. Surface hardening treatment of steel by heat or mechanical means to increase the hardness of the outer surface while the core remain relatively soft. Okay, we have to just hard the outer surface. On that time, we are trying to prefer the use surface hardening process. What happened is here, it may value for its low and superior availability in manufacturing. Mostly the oldest surface hardening method is carbonizing instantly placed at high temperature for several hours in a carbon carbon environment, and the Q into the surface of the steel, which rendering into it harder. Okay, another method of the surface hardening is nitriding, carburizing. After that, nitriding, where in the carburizing we are trying to use or diffuse the carbon, while nitriding is used in the camshaft or fuel injection pump, where we utilize the nitrogen and heat. And flame hardening and induction hardening, in which high heat is applied for a short time, high heat for a short time by gas flame or AC electric current. Okay, Okay, and then the steel is immediately quenched, which are used generally for larger implement. Mechanical means of hardening the surface of the steel parts include pinning, which is hammering of the heated surface, as by iron pellets shots onto the surface or by air blasting, and cold working, which consists of rolling, hammering, or drawing at temperature that do not affect the composition of steel, right? Mar tempering, or it may also known as a mar quenching, to overcome the restriction of conventional quenching and tempering. Therefore, use this process, or it called a mar tempering. Mar tempering permit the transformation of austenite to martensite to take place at the same time throughout the structure of the metal part. Residual stresses developed during mar tempering are lower. The stresses which produce in the mar tempering are lower than the developed during the conventional quenching. Okay, so that depends okay, which kind of application we have to require. Suppose we have to achieve the mar tempering process, or we have to read tempering is also reduce or eliminate susceptibility to cracking, right? It may reduce the cracking. Another advantage of the mar tempering in molten salt is the control of surface carbonization or decarbonization. Okay, and last one is the also known as and the hardness, but this requires a structure which are refined are very important. Okay, as we will as we were discussing the video also that how it may be helpful to heat treatment process.
Conditioning treatments can be used to obtain the final properties of a steel, or it can be used as an intermediate step in order to ensure that the material will not crack. Following rolling, casting, forming or forging. It can also be used to get the material into a state to aid in machining. In both normalizing and annealing, the material is heated to the austenite range and then slow cooled. This is done in still air for normalizing and in a furnace for annealing. A normalized structure can also be tempered to alter the properties slightly. Any gases that need removing, for example hydrogen, will be done as part of this process. Both treatments leave the material homogeneous, soft and ductile. But because normalizing is cooled in air, the strength and hardness of this structure will be greater than the annealed one. Some nickel alloys and stainless steels are used in the annealed condition to aid in corrosion resistance. Due to the slow cooling rates present in normalizing and annealing, a pearlite structure is likely to form. Pearlite consists of alternate layers of iron carbide, also known as cementite, and a pure iron structure called ferrite. During cooling, the austenite, which has higher solubility for carbon, starts to turn to ferrite. But because this ferrite cannot accommodate the higher concentration of carbon, the structure develops in alternate layers of cementite and ferrite. This perlite is often present with ferrite, and depending on the carbon content, the perlite and ferrite will be present in differing ratios. If the cooling rate is too fast for perlite, but not quick enough to produce martensite, a structure called bainite will form. Bainite is of medium hardness and lays at a medium cooling rate in between perlite and martensite. Initially, ferrite is produced, but because the cooling rate is quicker than perlite, the structure does not form in layers of ferrite and iron carbide, but instead, the iron carbide starts to precipitate from the remaining carbon-rich austenite, forming a structure that consists of ferrite and particles of iron carbide. Depending on the cooling rate, these iron carbide particles can be more elongated. This is called upper bainite and is the slower cooled of the two structures. The other, lower bainite, forms at faster cooling rates and contains ferrite with finer disc-like particles of iron carbide. An annealing process used in cold rolling or forming is a subcritical or process annealing. This is used to reduce internal stresses after manufacture or to enable further processing. In this process, the steel is not heated all the way up to the austenitic range, but is heated just below the ferrite to the austenite transformation temperature, usually around 500 degrees to 650 degrees Celsius or 930 degrees to 1200 degrees Fahrenheit. The material is then held for the desired amount of time to cause softening through structural changes, primarily grain recrystallization and grain growth. Generally, the higher the alloy content, the easier it is to form martensite, and this ability to form martensite is known as hardenability, meaning a steel with low hardenability requires a faster cooling rate to attain the same hardness at a given location than a steel with high hardenability. Knowing what structures will form in a steel can be aided by two diagrams called the continuous cooling transformation and time temperature transformation diagrams. Both these diagrams show what structures will be achieved under different heat treatment conditions. They will also show the effect that chemical elements will have on the structures formed. For example, elements like carbon, manganese, nickel, molybdenum, chromium and vanadium make the steel more hardenable, making it easier to form martensite at slower cooling rates. Time temperature transformation diagrams are used to understand what microstructures will form as a function of temperature and hold time. This means that heat treaters can use this diagram to understand what structures might be formed if a component is cooled from austenite and held at a given temperature for a given time. This is possible because if we hold austenite at a temperature where it is unstable, eventually austenite will form into a different microstructure, a process called isothermal transformation. The diagrams assist in conducting two treatments that help to minimize distortion, residual stresses, and risk of cracking. These are called mertempering and austempering, and they are essentially the same process. They involve cooling at a sufficiently quick rate to an intermediate temperature to form the desired structure, holding to enable the temperature at the center to equalize with the surface to reduce internal stresses, and then cooling the material to room temperature. For mertempering, the material is held in the martensite region, and in austempering, the component is held in the bainite region. A salt or oil bath is often used to hold a sufficiently high intermediate temperature. Time temperature transformation diagrams provide a good starting point to aid in heat treatment, but because they are interested in the isothermal transformation of austenite, they are only of limited use. To accurately predict the heat treatment response and thus microstructure of different steels of different sizes quenched in different liquids, we need to use a different chart called a continuous cooling transformation diagram. This has greater practical use for heat treaters. Continuous cooling transformation diagrams present data in two ways. The first is to plot microstructures as a function of temperature and cooling rate. From this, we can superimpose the cooling rate of our component either at the surface, center, or any distance in between, and we can predict which microstructure will be formed. The second is to represent the cooling rate at the center of different diameter bars for cooling in air, oil, and water. This type of CCT diagram is a convenient way to look up the bar diameter we are quenching and the cooling medium used, and again predict the structure at the center of the bar. Both of these ways are often presented on the same diagram, along with the hardness, and this will enable the heat treater to start to predict the properties of the steel. There are more specialized heat treatments that we have not covered here that use special processes and environments to control specific material properties. These processes include quenching with polymers and brines using surface hardening by just heating and quenching the outer few millimeters. Continuous furnaces can be used to automate the process, and special environments like in nitriding can also be used. So to summarize, heat treatment is critical in achieving the optimum properties and is used for either softening or conditioning a metal, like in normalizing and annealing treatments, or it can be used to harden a metal, like in quench and tempering, or age hardening. These treatments will produce three main microstructures, either perlite, bainite, or martensite. The specific heat treatment used in manufacturing will depend on the metal chemistry, the size of the part, and the required properties. Two diagrams can aid heat treaters in predicting the structure and properties in metals. These are called the continuous cooling transformation and time temperature transformation diagrams.
Very helpful video and very helpful PPT for you, which I'm trying to cover maximally with the basic introduction of heat treatment. Hope so. Please refer it one or two times, so it may very helpful to you. In the PPT, I will not. I'm not added any range or any alloy, but that may because that may added in the video. So I request to all that you refer this whole lecture in 2-3 times, so it may be very helpful to you to get the advantage regarding our chapter of heat treatment. If any query, then please comment in the comment box. Okay, stay safe, stay home. Thank you.